Okay, let's start with lecture 3 directly, okay, which is the operator view of rigid body transformation. So before I said it's a rotation matrix, for example, the definition we gave is not in terms of action. It's not in terms of rotating some frame or point. It's really given, it's a representation of a orientation of a frame, okay? Today we are take another view, which is the operator view of the rotation and rigid body transformation. Okay, that's I think it's the key to understand exponential coordinate and product exponential, those type of things for screw theory based robotic kinematics. Okay. So the whole lecture consists of several parts. We'll start with the rotation operator. I think the homogeneous transformation will be rather similar. And before we start, let's briefly recall the skew symmetric matrices. As I mentioned before, I think given any vector in R3, right, you can construct a skew symmetric matrix. In this class, we will use this square bracket to represent this matrix. This matrix is a 3 by 3. It has several properties. Okay, this is defined here. And the first very important property is if you take transpose of this matrix, you get a negative of itself. Okay, it's not symmetric, but it's a skew symmetric. Okay. Actually, there's a mathematical term that maybe I think is worth for you to let's say at least be aware of, which is the set of skew symmetric matrices is called the little SO3, for example. Okay, when we talk about R3, it's SO3. So SON consists of all the skew symmetric matrices in N by N, all the skew symmetric N by N matrices. Okay, if you remember that we call a rotation matrix, let's say rotation matrix, we say it belongs to capital SO3, okay, big SO3. And the skew symmetric matrices is not a rotation matrix. Okay, skew symmetric is not a rotation matrix, and it just represent the what? The cross product. And the little SO3 and the capital S3, they are of course different. This guy is all the rotation matrices. Is R transpose R equal to identity, and the determinant of R equal to 1. That's the criteria to be satisfied for SO3, capital SO3. Okay, what's the relation between this little SO3 and the capital S3? It's actually, this is really the matrix exponential map. Okay, that's what we are going to introduce today, right? All the things, I think there's many different ways. If you read the different textbooks, they will discuss differently. To me, I think it's very important, at least that I got really kind of understand a little bit better by taking this perspective, is really to take a differential or different equation perspective about the rotation operator. Let's start with very, very basic, okay? Physics, high school. Let's consider a point, okay? We think about rotation matrix. Now let's think about as action. You want to rotate something, okay? From initial point, you rotate about certain axis for a while, for a certain degree, and you end up with another point, right? And we want to consider this whole physical process. And we want to consider this process through a differential equation view. Okay, let's see how it works. Suppose I have a coordinate system, okay, and I have a rotation axis which is omega hat. When I say hat, typically it's a unit vector, tell you the rotation, the direction of the axis. Okay, suppose we're doing some kind of operation, rotating operation which is rotate, which is this is counterclockwise about this omega hat. Suppose initially we're let's say we are here. This is our initial point, which is a P of 0. Let's say this point follows this rotation motion, all right? And its motion will be described by a linear differential equation, right? Because this point follows differential equation, that means its linear velocity, this point that initially here, at any given time, it's here, going here, right? And at any given time, it's a P of t. And this P of t's linear velocity is nothing but the angular velocity cross this, the position or the vector of that. If you look at this more carefully, you will say, here, this is the origin, right? If you think about representing this point in this coordinate frame, this is the vector. And this point's linear velocity, if it follows a rotation motion, is omega cross this vector. If you think about this, is like from OP, this vector. Because we use this frame to represent this P, this will be the coordinate of that point. Okay, that's angular velocity. And this is the linear velocity at time t. That's simple high school physics. Any questions? Okay. At any given time, this guy is motion is described by omega cross the position or coordinate of this point, current position P, right? So at different location, the linear velocity is different, right? The linear velocity is different, but they all have to satisfy this same kind of expression. And we have learned cross is nothing but a linear operator, which can be represented by a matrix, which is skew symmetric matrix, right? This guy is our skew symmetric matrices. Let's say 3 by 3 is little SO3. Okay, it's a matrix times a vector. And we also know we start at time 0, it is at P0. So overall, you see we have a what? Stefan, what is this? You guys are together, okay?
I cannot say that.
Fuzhen, what do you think? I cannot hear them clearly. I will ask Fuzhen then. You can say Chinese if you want.
It's like
linear
linear system.
It's a linear differential equation, right?
Linear control system. It's also
we don't have a control. We don't have a control yet, right? So anyway, let's recall. Maybe you forgot. I don't know. Let's say we have our first lecture, right? Lecture 1 is ax dot equal to ax. That's a linear differential equation in state space form, right? This was a matrix, and this is the state vector, right? And if I say I have an initial state like this, Yinghan, what's the solution to this differential equation?
E to the power a t times x0.
So this xt will be e to the a times t
x0.
That's 0, right? That's what we derived. How do we derive or prove it? Based on uniqueness and what? Existent uniqueness theorem, right? So we check it satisfies differential equation, and also by definition of a matrix exponential, we verify that it satisfies differential equation. Okay, with this fact, let's recall this result. Now, what we have here is P dot T equal to skew symmetric matrix omega times T. At any given time, the position of the point satisfies this differential equation. Do you agree or not? Liu Xin, it's okay? Right? Anyway, you don't have the answer anyway, so that's fine. So this is, if you make analogy between these two, Yinghan, you can continue to answer what would be the solution of this guy's differential equation.
E to the power omega t times t0.
Okay, so that's essentially what? This one, right?
Yeah.
Our solution is this. Okay, just make pattern recognition, right? This A will be so A here is omega skew symmetric. This is a matrix, right? 3 by 3. So roughly speaking, let's interpret this math term in terms of, let me see. Let's interpret this equation. What's the physical meaning of this equation? So initially you are at P0, okay, and you follow a constant rotation about this direction, omega hat. For time t, you will be at here, right? And the angular velocity we're assuming here is a unit vector, okay? So roughly speaking, at the time t equal to theta, let's say some theta time, maybe 2 seconds or 3 seconds, and the point has been rotated actually by theta degree, because it's unit vector, then I would say, if I say rotate P0 about this omega hat axis by theta degree, I will have an expression of a P theta equal to that. Any questions? All right. So overall, you think before the rotation is P0. After rotate by theta degree is e to the omega hat theta times P0. So overall, we could call this guy a rotation operator, right? Operator. What do I mean by operator here? Let's just argue roughly. It just operates upon the initial point. P0, you multiply by this operator induced matrix. Then you get the point after the rotation. Okay, so overall, I will call this guy rot, okay, about omega hat, that's the direction, by theta degree is defined as the matrix exponential e to the omega hat theta, all right? So this guy can be viewed as a rotation operator that rotates a point about omega hat through theta degree. Okay, this holds, let's say this relation, all this discussion, the discussion holds for all coordinates frame, right? As long as I pick, this is basically physics. This is basically, I didn't say which coordinate system, but for holds for any, for let's say for any reference frame, you just need to pick one to express this physics, right? And but in the same time, you can say that you can see that to express this physical law, you have to pick one coordinate system for throughout the whole process. Okay, you cannot change coordinate. Otherwise, you may need to be careful about the change of coordinate things. Okay, so now let's think about this. So every rotation matrix actually can be viewed as a rotation operator. This is, I think this is a fact. I will call it a theorem, not a simple fact, okay? What did I say is that first of all, let's divide this in two parts, okay? I don't think this statement is very precise. Let's make it more precise. Any, I would say any matrix of the form, let's call that E omega hat theta. Okay, that's a very special matrix. It's obtained by what? It's taking a matrix exponential of a skew symmetric matrix, right? A very special matrix. For any matrix of this form, it always belongs to SO3. Okay, it's always a rotation matrix that we defined before. I cannot directly say it's a rotation matrix, right? I know this guy serves as rotating something by theta degree. That's an operator. And I haven't proved this guy will be can satisfy the requirement to be a rotation matrix that we defined in lecture 2, right? I'm not sure whether the logic, you have to make sure this. We defined the rotation matrix before as the orientation, and it satisfies the SO3 requirements. What is the requirement? R transpose R equal to identity, determinant of R equal to 1, right? That's our requirement. And so far we say the rotation operator of this form, but now this is a theorem. Any matrix of this form must satisfy this. Okay, this is the theorem. I don't want to prove that precisely, but we can argue. I think it's not hard. Fuzhen, can you prove this?
Yes.
Yes. Okay, let's just check one condition. Okay, I don't think we can prove everything. Let's just check this. Do you think, first of all, do you think E, this guy, theta, transpose times this matrix equal to identity? That's something we need to check first. Okay, let's do a first question. Let's do a first fact. Let's do it. Is that I would say this guy, right? Skew symmetric. Let's say theta take transpose, right? By definition, let's not use square. By definition, this is what? Identity plus this matrix theta, right? Plus 2 factorial this guy squared theta squared plus, right? Take transpose. Are you with me? Okay. If I take transpose, this is all summation matrix, I can move the transpose inside, right? So overall, I would say this guy is all about summation, let's say J from 0 to infinity, omega hat theta whole thing J factorial, right? Take transpose, we'll take this transpose. Move inside. And this is skew symmetric. Overall, I would say this, I'm not sure whether you can see, I will jump a few steps. This is nothing but this. If you take transpose, because there's a transpose, omega hat square transpose will be negative omega hat square, right? Look at this property. Transpose, you get a negative sign, right? So negative sign, you have this, right? So this guy is negative. So we also know the second fact is E, let's say E A times E the negative A should be identity, right? Because you can sum them. So because of this, we can conclude E to the this guy transpose, which will be negative times this height omega is identity. I quickly show the reasoning steps. It's also exercise of this matrix exponential and the skew symmetric matrices properties. Okay, and the second one, this by defining this, we also need to show the determinant of R is 1. This is a little bit tricky, I think. All right. First of all, E to the omega hat times 0 is identity, right? Are you with me? if I pick theta dot, this is theta is a scalar, right? Theta is, if I put 0, then it's e to the 0 matrix is identity. So determinant identity is 1. Okay, and also because of the continuity of the function in terms of theta, also the continuity of the function of determinant is always 1. All right, we can argue that way, but I don't want to go through all the steps. But anyway, we can show, I need to ask you, I don't want to, the only thing I want to emphasize, this one is not by default a rotation matrix. Okay, we have to close the reasoning loop saying that it satisfies the definition conditions that we used before. Okay, so far what we got is that as action rotating something by theta degree has this form. Okay, this operator, if you multiply by a point, that means rotate that point about omega hat by theta degree. Then we show this matrix operator is also in SO3. That's so far we have argued. Okay, it's also a rotation matrix that we defined before. Now we connect two things, right? The rotation operator is a valid rotation matrix from our definition before, but you can also define rotation matrix as this. Okay, there's this equivalent definition, but we start from a rotation matrix definition like this, right? X hat, Y hat, Z hat, right? That's our definition. We have to close the loop. This define in SO3 and definition here also in SO3. These two are equivalent definitions. Any questions? Let's clarify a few things. We have seen how to use R to represent frame orientation and change of coordinate. That's from lecture 2, right? Now we say that R, a rotation matrix, always, well, this form of rotation matrix can be think of a action or operator. Okay, these two kind of view of rotation matrix are completely different. One is a action, is a verb. The other one is a noun, is a 名词, it's representation of orientation. You see what I mean? Okay, these two are completely different. Okay, to apply rotation operation, all the vectors and the matrices have to be expressed in the same reference frame. This is quite clear from this equation. And basically, this equation can be thought of as a coordinate-free way of thinking about physics. Okay, it doesn't matter which coordinate you choose. Okay, and we can choose different coordinate to express this physics, but the bottom line is that you cannot use A and here use B. Okay, that's what I mean. You cannot do this. As long as you use same coordinate system, everything should be okay. I'm going to really subtle things in rotation matrix, and I think understand this, if we take a little bit more patience here, then later we can avoid a lot of mistakes. As my collaborator Pat Winsing said, it's most of the coding errors in robotics, at least in like locomotion controller design, is about rotation matrix. So you have to be super clear what this is about. Okay, let's give examples. I'm asking you to answer questions, so be careful. Fuzhen.
Yeah.
I gave these few numbers. This is a rotation matrix, right? Is this right?
Yeah.
This is rotation matrix. Okay. It can be used to represent a orientation of some frame relative to other. If I give these numbers, what the meaning of these numbers is really up to you. Here I can think of this as orientation of one frame relative to the other. I can also think about these guys as a operator action. In fact, in this case, it's rotate about x-axis by half pi. Okay. Either way, there are different views of the same set of numbers. Let me repeat: the numbers are the same, but the meaning are different. Could be different. That's very important. Okay, let's think about this for now. For example, let's think about this. If I say relation Q equal to R times P, I have a vector equal to R times another vector. I can interpret this equation in many, many different ways. Let's categorize these ways into two things, right? First is change of reference frame. Okay. In this case, I can think of this as change of reference frame. What do I mean by that? In this case, R is orientation of change of reference frames. This way, let me explain a bit better, okay? Change of reference means there's two frames involved. Let's say A and B. That means change of reference frame, you at least have two frames. And same or one, I would say one physical point. Let's call that P. So change of reference frame is that one physical quantity, either vector or point, its coordinates in two different frames are related by this relation. There are two frames, one point, okay? In this case, let's say R can be viewed as orientation of B relative to A. Okay, then more precisely, I should say, then in this case, then Q, let's say P and Q, let's say P and Q are the coordinates of the same, this is very important, the same points, okay? There's no 2 points, it's just the same point, 1 point. The same point in what? B and A. Okay. If I be more precise in this case, R is essentially, i.e., R here can be written more precisely or more explicitly is RB in A, right? Orientation of B in A. That's my notation before, right? So in this case, it's not a action, it's not operator, it's just a orientation of B in A. And we derived why this can be used to change of coordinate. So in this case, I would say I can call this, that's the same point. Let's call this point, same physical point. Let's call this point, same point. Let's call this point A, okay? Let's call this A. Then in this case, P is A in B, okay? And the Q, the number of Q means the same point in A. So Q equal to RP means A equal to, right, AA equal to RBA A of B. Again, in computer, it doesn't know what's going on. He only knows the numbers. There's a few numbers, a vector P, there's a vector Q, there's all these 9 numbers of R. The relation can be interpreted differently. The same relation here is 2 frames and 1 point, and the coordinate of this point in different frames are related by this relation. That's what change of coordinate means, okay? It will be completely different for a rotation operator interpretation, okay? Rotation operator interpretation is the following. Here, we only have 1 frame, okay? Here we only have 1 frame. 1 frame. 1 frame, then 2 and 2 reference frames. sorry, 2 points, sorry. Hold on. Yes, 2 points. And let's say these 2 points, and they are in the same frame. Let's say we have A and A prime. We have 2 points. And P, and let's say one frame, let's just call it A, okay? Or O, or whatever, let's call it A. So P and Q, P will be my A in A, and the Q would be my A prime in A. Okay, and how do we relate these two? Is that this is a rotate, right, by certain axes. Let me just use this operator. So rotate A, then you got another. You rotate this A, you rotate around certain axis, you get another A, which is A prime, and these two are related by this. Do you have any questions? I need to see you guys. Yinghan, do you have any questions? You guys are discussing.
No.
No? So in other words, I would say A of prime in A equal to the rotation operator. This is matrix, right? Let's call this matrix. Let's call it R, sorry. This is R, really means the rotation operator, and A in A. Fuzhen, any questions?
No questions.
Okay, then I ask you questions, all right? Anyway, I will save that later. You see that, okay, 1 frame, 2 points. There's a 2 frame, 1 point, okay? The same thing happens for, you can also think about this as a frame operation, but I think that's very similar. If you understand the point operator, then the frame is the same thing. This one, the change reference frame for a frame. Okay, so let's say we have one change reference frame is have one, not point anymore. Let's say one frame object. Okay, and the 2 reference frames. Sounds a little bit confusing. Okay. Suppose the frame object that we want to represent, frame object. It's let's call that frame object is A. Okay, and its orientation, let's say in O is what, Fuzhen? Let's say I have a frame orientation in O. I mean, if we have a more explicit notation, it will be R A in O. Okay, by definition, right? By definition, that will be the the x-axis of A, y-axis of A, and the z-axis of A, both in coordinate with respect to O frame. Okay, that's the orientation of A relative to O. Okay, and we also have the orientation of A relative to B. Okay, then I would say RAO is, let's call it RBO, RAB. Okay, that's basically the same as the change of coordinate for points or vectors. This guy is our R. Okay, that's also, think about this as a, did I write it wrong, or I think it's, well, notation a little bit bad. This is a bad notation anyway. So what I mean is that whatever I'm multiplying here, in this case, is a change of coordinate. Okay, whenever you think about change of coordinate, that R always represent the orientation of one coordinate frame with respect to the other coordinate frame. Okay, you can also think about as a action. So basically, then this is a similar thing. Similarly, we have two frames, two frame objects that we care about, and one reference frame. So what I mean is that what we got is that I have a frame A. That's my frame. Okay, that's a frame A. If I rotate about let's say certain axis, I will get another matrices, right? Suppose I don't know how to write. Maybe the same thing like this. Okay, this will be my A prime. Okay, if you rotate, will become A prime. So that will be from A. If you rotate, multiply by this R, you get A prime. You have two frames. That's, you think about frame as your object instead of one point. You rotate, you multiply by this frame, you got this A frame. So overall, you will say R A prime equal to R times RA. If I want to write more explicitly, so what's the reference frame here is typically, I can say more, if more, I would say more precisely, I would say this is RA frame. That's a frame orientation with respect to some kind of a common reference. Let's call it O, okay? That's R times RA O. So the orientation of A in O related to orientation A prime in O, and these two are related by R because R is the operator rotate that matrices. Any questions so far? All I want to emphasize, I think some people may got it and some people got a rough idea, and I think that require more exercise. You may overestimate your understanding about rotation matrices and make mistakes. Okay, so that's always think in your mind, rotation matrix can be a pose and also can be a operator, a action. Okay, that's the key. I will have a little bit more time, so let's move on. So that's how do we obtain the rotation operator? Okay, through differential equations. Now let's see how we represent this operation maybe in different frames. Let's make somebody a little bit more confusing. Before that, let's dive into a little bit more details about rotation matrix properties. First of all, let's say R belong to ISO3. That's a rotation matrix. By definition, it satisfies this, right? This is the definition. This is our definition. We somehow prove it, and this is actually one of the conditions for all the matrices in ISO3. Here's a typo. This is R2. So R1 times R2 equals to, is also, sorry, this means product. So if R1 is a rotation matrix and R2 is a rotation matrix, and R1 times R2 is also a rotation matrix. So this means product of rotation matrix, two rotation matrices is also a rotation matrix. Fujian, how do we prove it?
It can be proved by the definition.
By definition? What
Yes.
definition? ISO3 definition?
Yes.
Really? Maybe. Okay. Let me think. Anyway, yes, can be proved that definition. I'm going to skip this. Also, this guy, for any vector that's a P and a Q in R3, this roughly means, okay, this is nothing but, if I have 2 points on the rigid body, after rotation, now you think about this as a operator, okay? You rotate P and then rotate Q by the same amount around the same direction. You get two new points, right? This is a P prime, this is a Q prime, right? You operate these 2 points, and this equation means rotation operator preserves distance. So the same distance between the 2 points after rotation is the same. That's actually required for, that's why rotation operation is a rigid body operation. It's preserved orientation, preserves distance. How do you prove it? Fuzhen.
The determinant of the R is 1. So
I don't think that can be proven though. I can have a determinant 1. Anyway, this is also by definition. This is easy, I can go over it. It's like R P minus Q, right? That's the thing. If you take a square, it will equivalent to prove the square is the same, right? This will be what? Inner product, right? This is a P minus Q transpose R transpose times itself, which is R P minus Q. The property really matters is this guy's identity. It's not really the determinant of R is 1. This is nothing but because this guy is identity, then I have P minus Q squared, right? So it's really preserved distance. This guy means this rotation operation, rotation preserves orientation. The relative angle of 2 vectors after you rotate is the same, and those can be proved by just plug-in formulas algebraically, and this is also the case. I don't think there's a very kind of insightful way to prove this, but if you plug in all these elements, you'll find it out, right? What this means, if you gave me a vector, if I rotate it and then become another vector, I take a skew symmetric matrix of this guy, is actually the same as skew symmetry of omega and the pre multiplied by R and right multiplied by R transpose. Okay, you can algebraically verify this condition. This is pretty important condition. I think all of these, I think you need to remember. There's other conditions I didn't list. So these are quite important ones that I think you need to better understand. Okay, any questions? All right, with these properties, let's think about, we have 6 minutes. Let's think about a little bit more confusing stuff, okay? I want to represent the operator in different frames. What do I mean by that? Let's say I have this is my axis, omega hat. I want my action is whatever point you give me, I want to rotate this guy. This is P, I want to rotate to P prime. That's my physical description of the operator. And this physical description or the nature of this operation shouldn't change with respect to the coordinate frame we are choosing to work with. Let me repeat. If I choose different coordinate to represent these guys and the rotation operation, it should, I mean, they should give me the same result. Okay, the points still move to this point. You see what I mean? Right? But I can choose to work with different frames to express this rotation operator, and this operator in different frames will have a different some called numerical numbers or representations. First of all, let's say I have two frames. Here, my description doesn't depend on any kind of frame I work with. Okay, I can choose frame A to describe this physical operation, or I can choose frame B to work with this, to express this operation. And in these two frames, the rotation operator also has a different expression. First of all, this axis, the rotation axis will have a different, will of course have a different numerical values, right? Let's say this guy is my, this direction in A, and this guy is my direction in B. All right. And so in this case, this is a free vector, by the way. So this omega hat A equal to RBA, AB times, I think I write it wrong, right? RBA, right? BA. So omega B hat. Okay, there's a relation. Now let's derive the overall rotation operator difference. Okay, let's work with simple physics. Let's say approach 1. Let me finish approach 1. Okay, approach 1. Let's consider generically 2 points. This P, after you rotate, after I rotate, it becomes P prime. 2 points, because operator view, okay, we work with one reference, but there's 2 points. Okay, so in frame A, I have P prime A should be the rotation operator, let's say omega hat in A by theta degree. Let's notice a little bit awkward, means I use A frame to relate this, to describe this physical law. Oh, sorry, this is also A, right? The same point in A, everything is in A, from P to P prime. That's A frame, okay? And now I can also choose B frame. B frame will be P prime B equal to rot B, omega hat B, theta, and P of B. Okay. Fuzhen, what's the relation between these two things?
P prime A equal to RBA times P prime B.
Roughly, okay. So I want to relate this the same point and with two frame, and they are co-located. The origin are the same, but it's a different orientation. Okay, so this guy is the same as I can conclude P prime B equal to let's do that way. So RBA times P prime B, right? That will be my P prime A. Okay, equal to, let's say everything I want to move to B, right? So this is if I multiply this to this P prime B, then I multiply by this, right? So it will be RBA rot, let's say in B, I will skip the inside, right? Times P of B. Are you with me? Then this is RBA rot B dot I also want to move it back. This is PB. PB equal to RAB times P of A, right? So if I multiply the rest, so hold on. Now this guy becomes, this whole thing becomes R P prime A, right? So this P prime A equal to this whole thing times P A. I think I'm right? So this whole thing should equal to this guy. So overall, I would say rod A, omega hat A, theta, equal to RBA, rod omega hat B, theta, let's call it B, and RAB. That's exactly the formula we gave above. All right. Physically, what do you mean? Okay, you want to express this thing in frame B, then you are currently in frame A, right? The point is in frame A. You first need to change coordinate to frame B using that, then using rotation operator in frame B, then change back to frame A. You see what I mean? So physically, that's the whole thing, right? So oftentimes you may use this relation. If you think about operator view, if you choose change coordinate, this operator is a matrix representation, and that matrix has this relation between two different reference frames. Okay, I think that's about it for today. I encourage everyone to work on homeworks. Next time I think we'll talk about, finish this lecture, then we will start exponential coordinate, which is the essential part for kinematics.